The Busy Beaver function, denoted sigma of n, defines the maximum number of ones a Turing machine with exactly n states can write on an initially blank tape before halting. This function is the fastest growing function that can be defined purely through finite computational rules. A Turing machine is a mathematical model of computation, consisting of a finite set of states, a tape divided into cells, and a set of transition rules. The machine starts in a defined state, reads the symbol under the head, writes a new symbol, changes state, and moves the head left or right. Only machines that eventually enter a designated halting state contribute to the Busy Beaver value. The definition requires maximizing the output over the finite set of all possible n-state Turing machines. Determining the value of sigma of n requires solving the halting problem for all n-state Turing machines. The halting problem asks whether an arbitrary program will eventually finish or run forever. Alan Turing proved in 1936 that no general algorithm exists to decide this for all possible programs. Since the Busy Beaver function requires checking every possible n-state machine and confirming its halt status, no single algorithm can compute sigma of n for all n. If an algorithm existed to compute sigma of n, it could be used to solve the halting problem, creating a contradiction. This inherent undecidability is the source of its explosive growth, placing it outside the realm of standard computation.
The proof that sigma of n is uncomputable relies on a diagonalization argument, similar to the proof of the halting problem itself. Assume, for contradiction, that a total computable function f exists that calculates sigma of n for all n. We could then construct a new Turing machine, m sub f, that uses f to determine the maximum runtime of any machine with a given number of states. M sub f could then simulate and potentially modify the behavior of other machines. By constructing a machine m' that has n' states and writes more ones than sigma of n', we derive a contradiction. This demonstrates that no Turing machine can compute the Busy Beaver function for all inputs, confirming its non-computable nature. The growth rate of sigma of n dominates every total computable function f of n. For any function f that can be calculated by a Turing machine, there exists some input n such that sigma of n is strictly greater than f of n. This includes functions like the Ackermann function, which already grows faster than any primitive recursive function, and iterated exponentiation. Sigma of n is not merely large, it transcends the entire hierarchy of computable functions. It serves as a mathematical boundary, separating functions that can be calculated by an algorithm from those that cannot. This rapid growth is a direct consequence of its definition, requiring the maximization over an undecidable set of machines.
Related to sigma of n is the maximum shift function, often denoted BB of n or S of n in some literature, which measures the maximum number of steps or transitions an in-state halting Turing machine can execute before halting. While sigma of n measures output, BB of n measures time complexity. Since a machine must execute at least one step for every one it writes, BB of n must grow at least as fast as sigma of n. In fact, BB of n grows even faster than sigma of n. If a machine runs for t steps, the number of ones it can write is bounded by t. However, the relationship is not linear, and BB of n provides an even more dramatic example of uncomputable growth than sigma of n. The first few values of the Busy Beaver function are known precisely. Sigma of 1 equals 1, achieved by a machine that writes a 1 and halts immediately. Sigma of 2 equals 4, achieved by a machine that writes 4 ones. Sigma of 3 equals 6. Sigma of 4 equals 13. These values were found through exhaustive search and rigorous proof that no other n-state machine could exceed that output. However, the complexity explodes rapidly. Even for small n, the number of possible n-state Turing machines is immense, specifically 4 times n plus 1 to the power of 2 times n. Proving the maximum output requires eliminating all non-halting machines and proving optimality among the halting ones.
The exact value of sigma of 5 remains unknown, but its lower bound is already astronomical. The current best-known lower bound for sigma of 5 is 4098. The corresponding maximum shift function, BB of 5, is known to be greater than 47 million steps. The jump to sigma of 6 is even more dramatic. The current lower bound for sigma of 6 is greater than 3.5 times 10 to the power of 18,267. This number is so large that writing it out in decimal form is physically impossible. These lower bounds are established by finding specific, highly optimized Turing machines that halt after writing a massive number of ones. The rapid growth of the Busy Beaver function has profound implications for the limits of formal mathematical systems. Kurt Gödel's incompleteness theorems demonstrated that any consistent, sufficiently powerful axiomatic system, such as piano arithmetic, contains true statements that cannot be proven within that system. The Busy Beaver function provides concrete examples of such statements. For any consistent formal system F, there exists a number n such that the statement sigma of n equals k is true but cannot be proven within F. This is because proving the value of sigma of n requires proving that certain Turing machines run forever, which is equivalent to solving the halting problem for that specific class of machines. The unprovability extends to Zermelo-Fraenkel set theory with the axiom of choice, known as ZFC, the standard foundation for modern mathematics. It has been shown that the exact value of sigma of 17 is independent of ZFC. This means that ZFC cannot prove the true value of sigma of 17, nor can it prove any value is incorrect. If ZFC is consistent, then the statement sigma of 17 equals k is undecidable within ZFC. This demonstrates that even the most powerful known axiomatic systems are insufficient to determine the behavior of relatively small Turing machines, highlighting the inherent limitations of formal reasoning.
The Busy Beaver function reveals that mathematical certainty is bounded by the complexity of the systems we use to define it. While the function is perfectly well defined mathematically, its values quickly become inaccessible to proof within standard axiomatic frameworks. The existence of such a rapidly growing yet definable function confirms that the set of mathematical truths is larger than the set of mathematical theorems provable within any single consistent system. The Busy Beaver function serves as a benchmark for the power of formal systems, showing exactly where the boundary between provable truth and unprovable truth lies in the hierarchy of computational complexity.